Intermolecular forces are forces between independent particles. They are weaker than bonds, the intramolecular forces, but are still strong enough to influence important properties of bulk materials, such as the temperature at which phase changes occur, viscosity, and other similar properties. In general, the stronger the forces, the higher, for example, the melting and boiling points of substances are. These forces, as a group, are called van der Waals forces. Van der Waals forces can occur between any pair of particles, molecules, atoms, or ions. As an introduction, we will focus on attractions between different molecules of the same substance. There are three types of these forces: dipole-dipole interactions, London dispersion forces, and hydrogen bonding. Let's look at each one of these individually. Dipole-dipole interactions are the attractions between the oppositely charged ends of polar molecules. In a polar molecule, one end of the molecule has a partial positive charge, and the other end has the same partial negative charge. These opposite charges attract each other, and the like charges repel. But they are only important when the molecules are close together, as they are in liquids and solids. Dipole-dipole interactions are related to the dipole moment of the molecule, which measures the polarity of the molecule. In the table, we have a series of molecules that have similar molar masses and sizes, but differ in their polarity, or dipole moment. The more polar the molecule, the stronger the dipole-dipole interactions, and the higher the boiling point. Just as a side point here, the opposite is also true. The higher the boiling point of a substance, the stronger the intermolecular attractions are. More about that later. London dispersion forces occur between any two particles. For example, in a helium atom, the electrons on average are evenly distributed around the nucleus. However, at any particular point in time, both electrons may be on the same side of the nucleus. When this happens, the atom temporarily becomes polar. Once this temporary dipole exists, it influences the atoms around it. An atom close to the electrons will have its electrons repelled and create an induced dipole that will be attracted to the original temporary dipole. This pattern can occur in nonpolar molecules and in polar molecules. Polarizability is the word used to describe the tendency to have electrons distorted in this way. So London dispersion forces, or simply dispersion forces, occur between temporary dipoles. Two factors impact the strength of these forces. First, molecules that are long and skinny have greater polarizability compared to molecules that are short and fat, because the length of the molecule and its increased surface area makes the separation of the electrons easier. The second factor is shown on this slide. The table shows a correlation between the molar mass and the boiling points of the halogens and the noble gases. However, this increase in boiling point is not, strictly speaking, related to the mass at all, but is rather because the larger atoms and molecules have bigger electron clouds. So, the more electrons a molecule has, the more polarizable it is, and the higher the dispersion forces. The relative strengths of dispersion forces and dipole-dipole forces overlap significantly. When comparing different molecules, we need to take into account both types of forces. If two molecules have close to the same numbers of electrons, then dipole-dipole forces will be more important in determining relative boiling points, for instance. For example, think about the slide on dipole moments and boiling points we saw earlier in this video. The molecules were all close together in molar mass and number of electrons, so the differences in boiling points were due to the differences in dipole-dipole forces. However, if the two molecules are very different in their number of electrons, then dispersion forces will be more important. For example, the boiling point of iodine, a nonpolar molecule, was given as 458 kelvins in the last slide, well above the 373 Kelvin boiling point of water, a very polar molecule. This is due to the fact that water has only 10 electrons, while iodine has 106, making the dispersion forces in iodine much larger than in water, and larger than the polarity of the water molecule produces. This graph shows a graph of boiling point versus molar mass for two series of compounds, one polar and one nonpolar. For the nonpolar series, CH4, SiH4, GeH4, and SnH4, the boiling points follow the expected trend, with the boiling point increasing as the number of electrons increases. But the polar series, H2O, H2S, H2SE, and H2TE, has an anomaly. Water's boiling point seems abnormally high. If we look at similar series for hydrogen compounds with the halogens and with group 15, we see similar anomalies for NH3 and HF. What's going on? Hydrogen bonding is an extreme form of a dipole-dipole interaction. It occurs only when hydrogen atoms are bonded to small, highly electronegative atoms, in particular to fluorine, oxygen, and nitrogen. When a hydrogen atom is bonded to these three atoms, there's a large enough difference in electronegativity that the bonds are quite polar. Because the atoms, fluorine, oxygen, and nitrogen, are small, this means that there is a strong attraction to the electrons in the bond. So there is relatively little electron density from the bond around the hydrogen atom, which means that there is little electron density around the hydrogen nucleus at all. This means that the nucleus, the proton, is nearly bare and can be attracted rather strongly to any other electrons, usually an unshared pair of electrons on another molecule. Let's look a little more closely at this interaction in water. In the diagram of water, since oxygen has a much larger electronegativity than the hydrogen, 3.5 versus 2.1, the bond is very polar. This means that the hydrogen nucleus has very little electron density around it. This leaves the hydrogen nucleus free to be attracted to a pair of electrons on another oxygen atom, forming a hydrogen bond, a longer and weaker bond than the normal OH covalent bond. A fourth type of intermolecular interaction is between a polar molecule and an ion, called ion-dipole interactions. These tend to be stronger than dipole-dipole interactions because, rather than the interactions being between partial charges, as in dipole-dipole interactions, it is between a partial charge and a full charge. This is a significant force when discussing the solubility of ionic substances in water. We will talk more about this type of interaction in a later chapter. This slide shows a decision tree to decide what the most important force present in a situation is. The first question, are ions involved, separates out the ion-dipole interactions, if polar molecules are present, and ionic bonds, if they are not. If ions are not involved, then the next question, are polar molecules involved, separates dispersion forces, if they are not, from dipole-dipole and hydrogen bonding, which are separated by determining if hydrogen is bonded to nitrogen, oxygen, or fluorine. Remembering that all molecules have dispersion forces, and that hydrogen bonding is an extreme form of dipole-dipole interaction, we can summarize the types of forces this way. Molecules can have London dispersion forces only, or dipole-dipole interactions and London dispersion forces, or hydrogen bonding, dipole-dipole interactions, and dispersion forces. These forces are listed in order of their relative strength for molecules of about the same size, but you should remember that there is a lot of overlap when molecules are of different sizes and numbers of electrons. The final intermolecular force, which we will discuss in more detail later, is ion-dipole interactions.